Well, hi again, this is Al. This video is pertaining to more indoor air quality issues. As we get going through this series of videos, I will be referring back and forth to humidity, indoor air quality, and the such. And again, if it makes sense, it makes sense. I started this because I've had to explain these items over and over again. This one in particular pertains to an issue that I had on a building, but it wasn't this exact same equipment. So this was kind of built from scratch on the scenario that if you have this issue with 100% outside air, in other words, a negative pressure building, you got to get that building back to a very slight pressure, which is basically 0.001 inches of static, or about introducing about 2% of the required building volume back into it to positive pressurize it. As we keep going, you're going to hear me talking about the RCCD control, which is a very valuable control, especially in this case. So this is a 100% outside air unit, and we got issues both on the top end and the bottom end. What we're starting out with is the scenario on this thing would be the scenario, the formulas again, procedure, airstream potential. In other words, what's in that airstream if we happen to operate it at 400 CFMs per ton? Expected indoor conditions. What are you looking for? In this case here, we're going to be looking at 72 degrees dry bulb or sensible temperature and 50% RH. Dew point. Why is the dew point important? And our scenario is going to only say out of the 4,000 CFMs total for this 10-ton unit or 400 CFMs per ton, we're only going to need 1,800. So will this do it? You know, will this be able to maintain the capacity? What is at 1,800 CFMs, 120,000 BTU unit? What will this do with this condition? When we don't need cooling, and why? In other words, calculating the bottom. When do we shut this off? And then some conclusions. This is a 10-ton unit, and it's a 10-ton package unit. And this is an actual example, but I'm not using the same capacity or the same settings. We found that the unit was no longer used, but we also found that the building had a huge negative pressure. And we needed about 1,800 CFMs to bring the building to a positive state. The unit's around 120,000 BTUs. And the example I'm using is a 92.6 dry bulb, 74.4 wet bulb. That is actual outside ambient conditions or design conditions for 1% for Chattanooga, Tennessee. And I just picked it out of the book. Again, the basic psychrometrics. I will again be working with just strictly the total, which is the 4.5. I hope to produce other videos to use examples of the other psychrometric calculations. And again, these videos are more directed towards technicians and people in the field, but they help everybody. Again, this explains it more in detail. And we're using the top one, the total capacity of a system. Determining the capacity of the airstream. The system is a 10-ton roof-mounted package unit, single circuit, and I'm going to give it some help, 2 5-ton compressors. So it's actually a 2-stage unit, which will help out. Current airflow is designed at 4,000 CFMs when running. Again, this was an abandoned unit. It wasn't running. I decided to pick it out of there just to see, test it out, and go from there. This is actually the design point, and these are the numbers, and here's the critical numbers. If you look at it, your dew point temperature is 66.9. Enthalpy is 37.8. And in this case here, the relative humidity at that is 43%. Now, when we're dealing with these systems, we need to understand that where we're at and where we need to be is two different things. So the next thing is the design is 92.6, 74.4. So what's the preferred indoor air conditions we want? I would say I'm going to put into this in 72 degrees and 50% RH. And that's where in the world we want the design. Now on the psychrometric chart, that's about where it falls. So that just gives you an idea, but I want to come back to this. We must determine both extremes to make this work. Now on that design thing, if you go look, and the critical thing on this is the 52.4 degree dew point temperature. So we got to find out what our dew point temperature is, the airstream. If we don't have something in that airstream that's below that 52.4 degrees, we will not dehumidify. If you look, and we'll keep going with this. First thing, we need to find the dew point for the desired conditions. Why dew point? It's because the dew point, when you reach dew point, you're able to squeeze the moisture out of the air. This example gives you a 75 to 55 degrees, which had been on my part been a lot smarter because I could have used this. But what it is that at 55 degrees, it has the exact same amount of moisture as what it does at 75 degrees and 50% RH. So once we cool it down and we put that in the stream, it's going to suck that moisture out, have it condense on the coil or whatever you happen to have in it. So that's what we got to have. We got to be able to do that. We got to be able to match the systems as we're doing it. So when we start doing our calculations, we're going to be looking at the 4,000 CFMs times 4.5 times the difference in enthalpy. In this case here, the difference is at design outdoor is 37.8. And design indoor is 26.4 because we got to reach dew point. So if we look at that 18,000 is the 4,000 CFMs times 4.5. And the 11.4 is 37.8 minus 26.4, which gives us a total of 205,200 BTUs an hour, or 17.1 tons. So the airstream has more energy in it at the rate that we're moving the air than what the unit could handle. So it never could get down to dew point. But we're not worried about that because what we're doing is we only need 1,800 CFMs. So let's see what the work capacity on this at the max outdoor temperature. Well, now we know what the capacity of the unit is. It's 120,000 BTUs. We also know that there's a difference 11.4. So we take that 120,000, we divide it by 11.4, it gives us 10,526. Now we divide it by 4.5, so that tells us that we could do upwards of 2,300 CFMs of air and get it down to dew point on that coil as it's passing through there. So this is more than large enough for what we need to do. So what do we got? We have 1,800 CFMs times 4.5 times the 11.4 gives us 92,340 or just under 7.7 tons. Yes, this unit can handle it. It can handle it. Now, our next issue is going to run into. So we're going to run into the bottom. Now, remember, we're bringing in 100% outside air. This is at design at the top. There is a bottom. To ensure we maintain proper RH in the space, we need to ensure we don't go above 60%. Why is 60%? Well, ideal relative humidity in the space is 40 to 60%. We're starting out at 50%. We don't want to go above 60%. So dew point is what we're looking at again. We need to go back to the chart. 72 degree dry bulb, 60% RH. The dew point is 57.4. So we can shut down the cooling around 57 degrees. Now we don't also, one thing that people look at and they get worried about is overcooling the space if you're cooling down to that. But if you have a little product called the RCCD in place, you could set your bottom on your unit. And as she starts to get down to that point, it'll start unloading. And what we've seen about the overcooling is normally the TD across the coil is 8 to 15 degrees. Overcooling something that would be taken care of by the existing indoor heating units. And the reason being is that we're not going to allow this thing at 57 degrees. Normally your discharge is going to be around 35 to 36. But at 57 degrees, and we have the RCCD set at a 50 degrees or so saturated, our discharge air is going to be somewhere between 58 and 65 degrees. And in that case, all the indoor heating units will take care of it. The two conditions we're looking at is 52.4 saturated and 57.4 saturated. We look at the points, and here it is, 52.4. We got a 21.6 empathy. At the 57.4, we got a 24.7. So we take the 24.7 and subtract it from the 21.6, and that gives us 3.1. And since we're dealing with the 1800 times 4.5, it's 8100, or it's 25,000 BTUs on the bottom, the difference. So what happens with that? Well, the issue exists. There is an issue exists on the bottom, and I've already given up that the smallest component is 5 tons. That's 60,000 BTUs. These issues include humidity control, short cycling, and liquid slugging. The solution is an RCCD 410-3, giving us the unit the ability to modulate down to 18,000 BTUs. So now we got the bottom covered. And also what is it said on there is that the 410-3 will also give you the ability to maintain a saturated suction pressure / temperature on your coil. And the higher you got it maintained, the better off you are, as long as you don't go above dew point. The key is being in that sweet spot between dew point and freezing. And also with this case, with the RCCD, the key is to keep it as high as reasonable possible and still maintain the unit, because you'll extend the runtime, you'll get more dehumidification, everything will work better, and that coil will become saturated according to what the TXV is set for superheat. So the conclusions. You must know the dew point of the condition you're trying to reach. If you don't know where you're trying to go, how in the world can you get there? It's like taking a trip. If you're planning on going to New York, but you don't know that you're going to New York, how in the world do you ever get there? You must know the amount of OA needed, outdoor air needed. Controlling humidity in a building has several things that go on with it, and one is building pressurization. One common mistake service guys make is they shut off the outdoor air coming into a unit. And then whenever they put it back on, they don't know where to put the outdoor air. They don't know anything about it, but they shut it off and they throw that building into a negative pressure. A building will have a natural negative pressure, even with the stack effect, but you got exhaust fans, who knows what all. And I've seen before on grocery stores where the people didn't like the makeup air coming in, so they would shut it off and somebody would forget about turning it back on because it was too cool. They did not heat condition the makeup air. And what I told them, I said, the makeup air was in a closed circuited hood. And I said, what you can do is put an outdoor stat on it, know what you're trying to do for conditions, and then you could shut that makeup air off at a certain temperature. Then if a little bit comes in the building, you got enough heat in the building to make up for it. Or in the case of a restaurant that had an issue with both moisture dripping off the grills and all kinds of stuff, they didn't have any makeup air. So anytime you pull it into a negative pressure, all that air, moisture, and that's going to come in through areas where you don't want it to come in. By putting in a positive pressure, you're pressurizing it with conditioned air, and now you're going to mitigate it. You must know the level at which you're shutting the cooling down for humidity control. Again, 60%. We were looking at it, where we want to be. Also understand that hopefully I'll have a video coming out pretty soon that will deal with mixed air conditions. Whenever you're dealing with redoing the amount of outdoor air you're bringing into a system, how are you affecting the dew point within that system? Normally 10%, very little effect. But if you get up to 30 or 40%, let's just say that somebody says, hey, we got a pandemic and I want you to bring in 4 times as much outdoor air. You go up there and do that. Next thing you know, you got an issue inside because of humidity. Humidity has as much of an effect on the indoor health as what anything there is. You also must understand if your machine has the capacity to operate at the bottom. In this case here, we showed it didn't without the installation of an RCCD. RCCDs can be put on about anything you want. I just realized, and again, I've been doing this for a long time. I had a question say, hey, my frequency drive compressor can only go down to 35 hertz because of oil delivery to the top bearing in the compressor, which I already knew about it. So if you got frequency drives on standard compressors, you got to watch out. A standard Copeland compressor, the frequency drive can only go down to 45 hertz because of that reason. But in this case here, it happens to be built for a frequency drive, but it can only go down to 35 hertz. So that means if that's a 15-ton compressor, it's not going to even get down to 7.5 tons of capacity. It's going to be something above that. So what happens is if you need something below that, well, after thinking about it, going through all the numbers, an RCCD can be added to that. And now when you hit the bottom, the RCCD will take over as long as the line size on a split system is okay. And as long as everything else is set up, as long as you meet all the requirements, now that machine can operate even down to 8 tons or so. And that's critical. So what happens? Those are the things and the conclusions of this video. Now, honestly, it took me a lot less time to do this video than it did to put the information together. So I'd like any comments on that, give them to me. Hopefully just give them to me in private. I've had a lot of really nice notes from the other ones I produced. And for now, that's it. And I hope to keep adding it to that YouTube channel. And I ask everybody to subscribe, like, and go about it. And until we talk again, and hopefully it'll be soon, I say goodbye for today.